Hello everyone. So last time we defined what it meant for f of x to tend to L as x tends to A. So we said that meant that we can make the values of f of x as close as we like to L by making x sufficiently close to A. But we didn't care at all what happens when x equals A. So now we're going to talk about a couple of definitions that are similar, very closely related, and just a variance of this idea. So those are one-sided limits and infinite limits. Okay, so let's get started with one-sided limits. So let's suppose we have a function which is defined when x is close to A and on the left of A. So we don't care at all what happens on the right of A. We don't care what happens when x equals A. Maybe it's defined there, maybe not. We don't care. So we only care that f of x is defined on the left of A. And let's suppose we can make the values of f of x as close as we like to L by making x sufficiently close to A with x less than A. Okay, so we don't care what happens when x is bigger than A. We don't care what happens when x equals A. We just care that we can make the values f of x close to L as close as we like by making x close to A on the left. Okay, and in this case, we say that the limit of f of x as x approaches A from the left equals L. So notice that there are two pieces that are added from the definition we saw in the last section. So there is with x less than A, and then there is x approaches A from the left. Okay, so less than A and on the left are the two pieces added. But otherwise, more or less, the definition is the same as the regular two-sided limit we saw before. Okay, and we have the similar notation. We write the limit as x tends to A minus. So this little minus is saying that we are a little bit smaller than A. So A minus means coming from the left, or the inputs are a little bit smaller than A. So we have the limit as x tends to A minus f of x equals L, or f of x tends to L as x tends to A minus. So this indicates the left limit, so coming from the left. And sometimes people write, instead of x tends to A minus, they write x and then an up arrow A, or x up arrow A over here. But it's the same thing. Okay, so this is the left-sided limit. And as you can guess, we define the right-sided limit similarly, right? So we have the same notation, x tends to A plus, meaning we come from a little bit bigger than A. Limit x tends to A plus f of x equals L, or f of x tends to L as x tends to A plus. And the idea is the same. So we can make the values of f of x as close as we like to L by making x sufficiently close to A with x bigger than A in this case. So it's the other way around. And we don't care at all in this case what happens on the right and what happens when x equals A. For left limits, we care what happens when x is less than A, and for right limits, we care what happens when x is bigger than A. Okay, so already we have three definitions, so it's getting a little confusing. What's the relation between them? Okay, there's a very useful fact that the two-sided limit, the one we saw in the last video, exists if and only if both of the one-sided limits exist and they're equal to the same number. Okay, so the two-sided limit equals L if and only if both of the one-sided limits equal L. And why does that make sense? Okay, if we just think back to the definition, what it means again, the two-sided limit means we can make the values of f of x as close as we like to L by making x sufficiently close to A, and x could be on either side of A. So in particular, if we are close to A and on the right, then we're going to be close to L, and if we're close to A and on the left, then we're also going to be close to L. So the top will give us the bottom. And then vice versa, if we start with the bottom, well, this is telling us that if we're close to A and on the right, then we're going to be close to L, and if we're close to A and on the left, then we're going to be close to L. Okay, so if we're close to A, then on whatever side, we're going to be close to L. Okay, you can make this rigorous if you want to be a mathematician and have, the rigorous definitions, but for us, this is good enough. Hopefully, it's reasonably clear. The two-sided limit equals L if and only if both the one-sided limits equal L and they are equal. And this fact is useful sometimes, for instance, if you have functions which are defined in cases. So we'll see an example of this in a second. Then it's easier to analyze, say, what's happening on the right side of a point and what's happening on the left side of a point separately. Or this is an easy way to tell you when a limit does not exist, right? If the two-sided limits are different, then the two-sided limit does not exist, right? If each of these are different, then the two-sided limit does not exist. Okay, so let's see one of these examples of definition by cases that I talked about. So here we have a function f of x. It's equal to x if x is less than 1. It's equal to 1.5 if x equals 1, and it's equal to x plus 1 if x is bigger than 1. Okay, it's kind of a strange function, but I cooked it up as an example. So the graph is something like this, right? If x is less than 1, then it looks like f of x equals x. It looks like y equals x. Okay, at x equals 1, then here it has the value 1.5. And then if x is bigger than 1, it's x plus 1. So it's like the graph of y equals f, but shifted up by 1. Okay, and as you can probably guess, we're going to look at what happens with the definition in each of these cases. Okay, so I claim the limit as x tends to 1 from the left of f of x equals 1. Okay, so I see if x is a little bit less than 1, and x is approaching 1. Okay, if x is less than 1, that means we're on this piece of the graph. If x is getting close to 1, then we're moving up towards this point. Okay, at 1, f of 1 equals 1.5, but we don't actually care. Remember, when we're taking limits, we don't care what happens at the point. Okay, so we're moving up to 1 from the left. Okay, what's happening to the y value? The y value f of x is approaching 1. Okay, so the limit as x tends to 1 minus equals 1. And then the same thing with the limit as x tends to 1 from the right. Okay, so if we restrict to being a little bit bigger than 1, we look on the graph, f of x, the y values are up here. Okay, and as we are approaching 1 from the right, that means the x values are going down. Okay, the y value is approaching 2. So the right limit of f of x equals 2. Okay, and then as we just talked about, in this case, the left limit and the right limit differ. So that means the two-sided limit cannot exist. So the limit as x tends to 1, f of x does not exist. Okay, and just to emphasize here, f of 1 equals 1.5, but that doesn't tell us anything about limits, right? With this strange function, the left limit was 1, the right limit was 2, the two-sided limit didn't exist, none of the limits was 1.5. Okay, so getting the limit by plugging in only works for a very special class of functions that we'll see later are the continuous functions. Okay, so don't just plug in unless you know that it's justified to plug in. Okay, so let's look at infinite limits next. So what is the idea of infinite limits? So again, f of x is supposed to be defined when x is close to a. So now we're looking at two-sided again, but we're not going to be approaching L, we're going to be approaching infinity. So f of x is defined for x close to a. We don't care what happens at a. And in this case, suppose we can make the values of f of x arbitrarily large by making x sufficiently close to a, but not equal to a. So again, we don't care at a. So here it's kind of like the usual definition of f of x tends to L as x tends to a, except arbitrarily close to L became arbitrarily large. Okay, so that kind of makes sense, right? What does it mean? I mean, it doesn't mean anything to be arbitrarily close to infinity. So in that case, the best thing we can say is we can make f of x arbitrarily large. And we're doing a two-sided limit, so we just say x is sufficiently close to a. Okay, then we say the limit of f of x as x approaches a is infinity. And we write the limit as x tends to a, f of x equals infinity, or f of x tends to infinity as x tends to a. Okay, so it seems like there are a lot, but keep in mind they're all based on the same kind of principle, right? We can either make f of x arbitrarily close to L in the case of finite limits, or f of x arbitrarily large in the case of infinite limits by making x sufficiently close to a. Or if we want right limits, we have to add and on the right. And if we want left limits, we have to add and on the left. So they're all they have the same building blocks. So don't think of them as lots of different definitions, just take the building blocks. And while we're doing this, I have to make a warning that I'm hopefully going to make more than once. Here there is infinity, and it's tempting to play around with infinity. But infinity is a symbol, it's not a number, so things like infinity minus infinity and infinity over infinity don't make sense. I mean, please just take my word on it, but if you want to ask, like, why can't I do that? If you think of two functions, f and g, and suppose f tends to infinity and g tends to infinity, and then you want to look at f minus g, so you have a function that goes to infinity minus a function that goes to infinity. What happens to f minus g? Well, anything could happen. It just depends on what's happening with the individual functions f and g. So you can't say anything about infinity minus infinity in general. It just doesn't make sense. So if you find yourself writing infinity minus infinity, infinity over infinity, you've made a mistake. Please go back a few steps and ask someone if you're stuck. Okay, so as we said, there are a lot of building blocks of these definitions, but they're all based on the same thing. So there are a couple more variants. So similarly to how we just defined the limit as x tends to a equals infinity, we can define the limit equals minus infinity. So what would that mean? It would say we can make the values of f of x arbitrarily large negative. So that means we can make them less than minus 100, less than minus 1,000, less than minus 1,000,000. We can make them as large negative as we like, provided we make x sufficiently close to a, but not equal to a. Okay, and then we can take those infinite limits we just defined and restrict them to limit as x tends to a from the right, and then get plus or minus infinity and limit as x tends to a from the left. The only things we add are x is larger than a and x is less than a. Okay, so we have a lot, but keep in mind the building blocks, right? Either f of x is getting close to L, or f of x is getting large positive and large negative. And we're making x close to a, or x close to a from the right, or x close to a from the left. Okay, so let's see a couple of pictures about infinite limits. So for instance, if we look at y equals 1 over x squared, then I claim that with this one, the limit as x tends to 0 of 1 over x squared equals infinity, and this is the two-sided limit. Why? So if we remember back what this definition of this infinite limit meant, it says that we can make the values of our function as large as we like, provided we make x close to a, or in this case, x close to 0. Okay, and that's true. So what does it mean to say on the graph that we're making the values of the function as large as we like? So it's saying however large a number we pick up here, however large a number we pick on the y-axis, and we draw this dotted blue line through it, this is, say, y equals whatever. However high up we place this line, we can make the values of the function lie above this line. So I have these points on the graph, provided x is close enough to, in this case, to 0. Okay, and that's true, right? I see that if I'm in this small interval around 0, then I'm going to be above this blue line. Or if I make the blue line up even higher, as high as I want to make it, I can make the graph lie above it, provided I am close enough to 0, right? So I can make the values of the function as large as I like, whatever line I place here, provided I restrict to x close enough to my limit point, which is in this case 0. Okay, so here we have the limit as x tends to 0 of 1 over x squared equals infinity. Okay, but what about 1 over x? Why did I pick 1 over x squared? So 1 over x is a little bit more complicated. So here is the graph of 1 over x. Remember, right, if x is close to 0 and positive, then 1 over x is very large. But if x is close to 0 and negative, then 1 over x is very large negative, so the graph goes down. So I claim that in this case, the limit as x tends to 0 from the right of 1 over x is infinity, and the limit as x tends to 0 from the left of 1 over x is minus infinity. So let's untangle why that's true. So if we're looking at the first one, a limit being infinity, that means however large we want to make the values of the function. So here is a blue line, and I could make it as high up as I want. We can make the function lie above that, provided we make x sufficiently close to 0 and on the right of 0. Okay, and that's true in this case, right? If I want the graph to lie above this blue line, I can do that if I make x close enough to 0, say in this interval, provided x is bigger than 0 and inside and close enough to 0, right? So if x is close to 0 and larger than 0, my graph's going to be up here. I have infinity. But notice I couldn't do two-sided limit in this case, right? If all I know is that x is close to 0 and I'm on either side, then I can't guarantee that the function is large because the function could be down here, and then it would be large negative. Okay. And a similar kind of argument works for the limit x tends to 0 minus of 1 over x is minus infinity. So what did this mean? This meant that we can make the values of our function as large negative as we like, provided we make x close enough to 0 and on the left of 0. Okay, so if we want to make the value as large negative, what does that mean? It means however far down we want to draw this horizontal line, forgive my picture, however far down we want to make this horizontal line, we can make the graph lie below that, provided we are sufficiently close to the limit point and on the left. Okay, and that's true, right? If I want to lie below this line, that works as long as I'm, say, this close to 0 and I'm on the left of 0. Okay, and two-sided wouldn't have worked because if I was on the right, I would have been up here. So for 1 over x, we really needed the one-sided limits to make any kind of sense of it. Okay, here is another example with natural logarithm of x. People get confused with the graph of natural logs. So I think it's always worthwhile reviewing. So it's defined for x bigger than 0. When x equals 1, it's 0. As x tends to infinity, it goes off very slowly to infinity. It's a very slowly increasing function. But when x gets to very close to 0 and on the right, it goes to minus infinity. Okay, and it's not defined for x less than 0. So this is an example where the limit as x tends to 0 from the right is equal to minus infinity. The limit on the left is just not defined at all. Okay, so a useful convention that we're going to follow in this course is that we say a limit exists if and only if it exists as a finite number. So that does not include infinity and minus infinity. Okay, so by limit existing, we mean the limit equals L, where L is some finite number. Okay, now we have vertical asymptotes. So a vertical line, x equals a. So remember, there are horizontal and vertical lines. Vertical lines are x equals something, and horizontal lines are y equals something. And remember that if you want to specify the equation of a line, you have to specify, so it's an equation, it's not just a number. So if you're ever asked to find an asymptote, you're looking for something that looks like x equals or y equals. Okay, so here we have vertical asymptotes. So these are of the form x equals a. We say that's a vertical asymptote if at least one of the following four limits is 0. So basically is infinity or minus infinity rather. So basically we're saying that at least one of the one-sided limits is plus or minus infinity, right? So we're looking for a number So we're looking for a number a where if we take the limit, we get plus or minus infinity. So x equals a is a vertical asymptote if at least one of the one-sided limits at a is plus infinity or minus infinity. So we're looking for what we have to plug in to make the functions grow arbitrarily large to infinity. For instance, here, a simple example, if we look at y equals 1 over x minus 1, if we take the limit at 1, okay, if we think about what happens on either side of 1, one way to think about it is it's a shifted version of 1 over x. Or if you just want to argue from first principles, if I take x a little bit bigger than 1, x minus 1 is going to be a little bit bigger than 0. I have 1 over a number that's a little bit bigger than 0. I'm going to get something very large. And then the opposite on the x less than 1. Okay. So in this case, we have the limit as x tends to 1 from the right is infinity. The limit as x tends to 1 from the left is minus infinity. Okay, even if we just had one of these, we don't have to have two of them, but even if we just had one, that would be saying that the line x equals 1 is a vertical asymptote to the curve. Okay. So hence x equals 1 is a vertical asymptote to y equals 1 over x minus 1. Okay, here is another example. If we think about y equals tangent of x, so that's sine x divided by cosine x. Okay, it has this weird graph because if we think about what happens as we approach, say, x equals pi over 2, we have sine x over cosine x. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So as we approach pi over 2, the numerator, which is sine, is approaching 1. The denominator, which is cosine, is approaching 0. But it's approaching 0 from the positive side. So it's going to shoot off to plus infinity. And then the same thing over here. As we approach minus pi over 2, sine is approaching minus 1. Cosine is approaching 0 from the positive side. So this is going to shoot off to the negative. And we can see, right, at pi over 2, there is an infinite limit as we approach pi over 2 from the left. And at minus pi over 2, there is a negative infinite limit as we approach minus pi over 2 from the right. Okay, so at both x equals pi over 2 and at x equals minus pi over 2, at those points we have an infinite limit. So these are going to be vertical asymptotes of our curve. Okay. So that's everything I wanted to talk about in this overview of infinite limits and one-sided limits. Hopefully the ideas are clear. So we started with the main definition of a limit that we talked about last time, but then we added on a couple of variants. So one-sided limits, limits from the right and left, they were the same as before, except the thing we needed to add was restrict to x bigger than a and restrict to x less than a. And then when we talked about when we talked about infinite limits rather, instead of having f of x get arbitrarily close to L, we were making the values of f of x get arbitrarily large. So there are a couple of building blocks of the definition, and it's all about substituting in the right pieces in the right place. Okay, that's all for today. Thanks everyone, and see you next time.